Okay, Bismillahirrahmanirrahim. Power system protection. And today our topic is protection of induction motor. So this is our new chapter. So let's start. Okay, so as we know that large induction motors are used to drive water pumps, fans, and other auxiliary items used in the industries as well as in power generating plants. So we know that in industries like rubber industries, the plastic industries, the induction motors are extensively used. Similarly, power generating stations, we have the forced draft fan, that is FD fans, induced draft fans that are ID fans, and some other auxiliaries used in primary crusher and secondary crusher house induction motors are widely used. Therefore, loss of motors because of any fault in the motor may be because of the winding fault, that is electrical fault, or mechanical fault that lead to the loss of the protection, in turn finally result in the loss of revenue. Hence, protection of induction motors is very important and essential for satisfactory work of the motor, as well as satisfactory working or production of the industries or power plant. So the type of protection scheme applied to the induction motor that are mainly depend on three factors. Okay, the first factor, that is the size of the induction motor. The second is the importance of the induction motor, and third are the load connected to the induction motors. So for example, if we say fuses, those fuses are adequate to protect small motors that are used in some unimportant or to drive some unimportant loads, say for example for household applications. Okay, so whereas if I use the induction motor at 6.6 kilovolt or in some auxiliaries in large industries, so and large generation power plants, then in that cases we need to give a separate sophisticated uh, and separate sophisticated digital or numerical relays protection based on that protection, so that if any fault occurs, then that can be easily detected. So now let us discuss what are the faults and abnormal conditions in induction motors. So the majority of the fault in the induction motor, that is because of the failure of insulation, that is electrical fault, and the other type of that are mechanical fault because of the mechanical failure. So the main cause of the failure of motors, that is because of extensive heating. Okay, so if this type of heating is sustained by the motor for a longer duration, then the motor will finally burn out. Overheating also reduces the lifetime of the motor. For example, if the motor is continuously overheated, say 10 degree above the specified temperature, uh, specified temperature in the data sheet by the manufacturer, then its life uh, its life can be reduced by almost 50%. Okay, these are the faults and abnormal conditions in induction motor. The For example, these are listed over here. The first one is known as overloading. Okay. The second is known as the single phasing. So one of the phase of the induction motor in three phase that is not there, then this will be not available. The third, that is known as phase unbalance. So instead of giving a red, yellow, blue, we will give some other phase sequence, or instead of red, yellow, blue. Okay. Red, blue, yellow. Okay, so this is actually the phase unbalance. Instead of red, yellow, blue, if we give a red, blue, yellow, so this means there is a phase unbalance condition. Okay. So and the phase reversal, that is also there. So and the fifth one is short circuit. If any fault occur in the winding, then short circuit is there, and large magnitude of the current will be flows in that condition. Okay. Uh, the next one is the arc fault, that is between the winding and the core of the induction motor. The next one is the stalling or rocked rotors. So any induction motor, when you start the motor, and if the motor denies to start, or if it started, then it is just running at a low speed than the normal speed, then this type of phenomena is known as stalling. Okay. And the last one is the underload. So let us discuss each and every phenomena one by one. Okay. So let us start with the thermal overload protection. The number given to the thermal load relay is 49. So the thermal overload element that is accomplished by modeling or image modeling of the motor, and that is accountable for all thermal process in the induction motor. Maybe when you start the motor, or when you run the motor in normal condition, or run uh, the start, or when you run the motor, or start the motor, or you start the motor in overload condition, or in stand still condition, that is the stop condition. The basic function is to operate the motor within its prescribed temperature limit, that is known as thermal limit of the motor. Now, the acceleration curve gives that the induction motor, whenever any acceleration curve is defined or given by the manufacturer, then it specifies that the induction of an account of current and the associated time for the motor to accelerate from the stop condition to the normal condition. So okay, so when you start the motor is at standstill condition. So when you start the motor, and after getting some speed, final base speed, whatever the time required by the motor, that is known as the acceleration time period. And this time period is always associated with some voltage, whether you start the motor at rated voltage or some reduced voltage. For large motors, two acceleration curves are specified by the manufacturer. The first, that is the at the rated voltage, 100% voltage, and the second is at the 80% of the rated starter voltage. So soft starters are commonly used in the induction motor to reduce the amount of inrush current or starting current when you start the motor, because when you start the motor, starting current of the motor is 5 to 6 times of the full load current. But keep in mind that this is not a fault current. At the start, the current is 5 to 6 times of the total load current. So this is not the fault current, and whatever device you use, it is capable to discriminate between these two phenomena. Okay, so the three-phase motors are designed such that the overload are just below the specified withstand value of the motor. The motor thermal limit curve consists of the three running conditions of the motor. What are these three conditions of the motor? The first one is the log rotor or standstill condition or stall condition. The second is this motor, that is acceleration condition, and the third is the motor that is running with overload condition. So ideally the curves, all the three curves should be provided for both hot and cold running of the motor. So these are the curves. Okay, so if I just look at the curve, then you can see that the first curve, that is the the first curve is the A curve, that is provided when you start the motor during cold condition. Okay, and it is running, and it is in running condition with overload. So cold running overload, curve A. So the just below this curve you have another curve where the motor you run with hot condition, and this is also the overload condition. So the curve B is hot running overload curve. The other two curves, that is the curve C and curve D, you can see that these are the acceleration curve for the motor. One is C at 80% of the starter voltage, and D is the 100% of the rated voltage. So when you consider the setting of the relays, then you need to consider the acceleration curve with 80% of the rated voltage. Okay, so let us see how we can apply the thermal overload protection in case of induction motor. Okay, so as I have told you that 49 is the number used or specified for the induction motor. So you can see this is the curve of the induction motor, where x-axis you have the starter current, on the y-axis you have the time. So now you can see that there is a curve known as motor thermal limit curve. Motor thermal limit curve. So by this curve, that is the darker curve, this is the motor thermal limit curve. Okay. So the thermal relay characteristics that should exactly match with the motor thermal limit curve, and it should be below, just exactly below this curve. Okay, so because if this curve is above the thermal limit curve, then the motor or insulation of the motor may burn. Okay, so thermal limit curve and thermal relay curve. Okay, so thermal limit curve should be above the thermal relay curve. So it should be exactly below, and it should not be very low with reference to the motor thermal limit curve. Otherwise, motor cannot fully exploit its overloading condition, because motor can easily withstand few percentage of overload condition. So thermal relay curve, that is 49 curve, you can see that is the exactly below the motor limit curve. Okay, so you can also see that just below that I've shown the starting motor starting curve. Okay, this curve. So I just observe this curve, the starting curve. When you see that this curve is nothing but the motor starting curve, so when you start the motor starting curve should be below the thermal relay curve, that is 49 curve specified by the manufacturer. Along with this, you can also see the another two curve. One is the inverse time over current relay, that is 51, again for the short circuit in the induction motor, and another is the instantaneous relay curve, that is number 50. Both 50 and 51 are used for the protection against short circuit in induction motor. So this curve, this 51 curve, that should be always separate with the motor thermal curve. Okay, now the next phenomena, that is known as a protection against unbalanced currents. Okay, so and this unbalanced current, the main number given to the unbalanced relay, that is the 46 number. Okay, so this type of relay is also known as negative phase sequence protection or negative phase sequence scheme. So when we say that in case of the unsymmetrical faults that may occur within the motor or the or on the feeder side, that is near the motor, then that may produce unbalanced voltages, and hence finally current become unbalanced. So the typical condition that can give rise to unbalanced currents are, the first one is the single phasing due to the disconnection of fuse for large motors. Okay, and this can be because of the disconnection of the fuse or the large motor. And the second, that is the unbalanced fault condition and the failure of breakers. So because any of these two reasons, the unbalanced current may produce and motor has to be protected against such unbalanced current. So now why motors need to be protected against unbalanced current? Okay, so this is because in this situation draws very high current because of the single phasing, hence its winding will be overheated, and which lead to deterioration of insulation, or sometime in the worst cases damage of the insulation will occur. So in case of unbalanced current, negative sequence current, that is I2 is produced, which may overheat or damage the rotor structure. It is written or specified in the literature that the heat produced because of the production of negative sequence current, that is 6 times the heat produced by the motor when positive sequence current flows. So to protect the motor against such type of unbalanced negative sequence relay, 46 that is used. So 46 relay is used. Okay, however, for small motors, phase unbalanced relay is usually used because because it is economically viable to use negative sequence uh, the negative sequence current. Okay, so in negative sequence phase sequence relay, each motor is designed for a specific permissible unbalanced current according to the standards. So the general equation for for allowable negative sequence current, that is given by I2 square times T is equal to 40, where I2 is the negative sequence current and T is the time during which the negative sequence current flows through the winding of the motor. So the other philosophy, suppose if I have a small motors and its cost is low compared to other motors, then it is not economically viable to use the negative phase sequence relay for protection against unbalanced currents. So in that case, we may use the definite minimum time delay relay, or sometime called inverse time definite minimum time relay. So if I use the definite minimum time delay relay, that is MDT, then the first stage of negative sequence protection that is given or covered by this relay, DMT relay, in the second stage of the unbalanced current protection, that is covered by the IDMT relays. Okay, these are inverse definite minimum time delay relay, IDMT. Okay. Okay, the typical setting range of the relay, that is I2, is in the range of 10% to 50% in steps of 5%. Okay, 10, 15, 20 in the step of 5% means 10, 15, 20, 25, and so on. Okay, so at this and this range, that is with the reference to the rated current of the induction motor, usually it is CT secondary current. Okay, sometime if I use the negative phase sequence current, that is 46 relay, then its setting, that is to be decided on based on the ratio of negative sequence impedance Z2. Okay, Z2 to the positive sequence impedance Z1. So you take the ratio of Z2 by Z1, and whatever figure comes, then you decide the setting according to the setting range given. In this case, the setting range given is 10% to 40% in step of 10%. 10 to 40% in the step of 10%. Okay, so this is for which relay? 46 relay, whereas this is for 46 relay, and this is for DMT or IDMT relays. Now the next type of protection or phenomena, that is known as protection against phase reversal. So instead of giving red, yellow, blue phase sequence, if the phase sequence is altered or changed, then motor need to be protected in that case. So for that, the relay number given to the protective device, that is 47. Okay, 47, protection against phase reversal. So the induction motor negative sequence current if there is a change in the phase sequence in the supply circuit of the motor. So in this situation, motor will run in opposite direction. The load, whatever you have connected with the motor, that is designed to run in specific direction only. So if the motor run in opposite direction, then whatever load you have connected, that will be damaged. So protection against phase reversal, that is very important, and this is once again achieved with the measurement of negative phase sequence current, that is the I2. Now for the next part of next phenomena, that is the protection against against the short circuit, and this is basically phase to phase fault. Okay, protection against phase to phase fault, and the relay number, that is known as 87. So for for short circuit in starter winding of large induction motor, maybe beyond 1000 kilowatt differential protection is used. So whereas if I have a small or medium range induction motor where we cannot use the differential protection for the protection against short circuit, there we can go for IDMT relay or other type like instantaneous relay, because this relay are cheaper than the differential relay. So for the large wattage, we are using this 87 relay, or if for the small rating or medium rating, we are using uh, the differential. Okay, so in order to minimize the burden and also to reduce the error due to long cable run, three current transformer are placed within the switch gear, and one CT is located in the neutral connection of the motor. Okay, in order to minimize the burden and also to reduce the error due to long cable run, three CTs are placed within the switch gear, and one CT is located in the neutral connection of the motor. Now for the small motors, as I have told you, phase fault protection, that is achieved by the overcurrent relays IDMT or instantaneous instead of the differential relay. The pickup of the relay is to set above the maximum starting current of the motor. Otherwise, relay may maloperate uh, as soon as you start the induction motor. Okay, so if the setting is below the maximum starting current, then sometime if it is not possible to go for or to reduce the setting of the overcurrent relay below the starting current of the induction motor, then a certain type of interlocking need to be provided. Okay, however, if you start the induction motor, any fault is there, then such type of fault, such type of the relay is not capable to detect the phenomenon. Okay, so protection against phase fault in modern digital relays, that is normally dealt with the differential relay and typical setting, that is 400 to 200,000 of the relay rated current. So this setting is normally for instantaneous relays, instantaneous over current relays. Okay, instantaneous, overcurrent range, this range. Okay. Okay, now the next one is the protection against stalling or lock motors. So we will discuss this in our next class. Okay, thank you.